Hello, welcome to this video. Now we will see how do we get the values of the parameters theta naught, theta 1, theta 2 such that the value of the cost function g of theta is minimum. We will use gradient descent algorithm to get the values of these parameters. Gradient descent initially sets random values to these parameters and by using the update rule updates all the parameters at once simultaneously in a single iteration of the algorithm and then checks if the cost function is minimum, and if it's not, then it runs the algorithm again as long as the value of j theta is minimum. So the update rule of gradient descent is written as theta j. This is the assignment. The previous value of theta j minus alpha times partial differential with respect to theta j of the cost function. Whereas j goes from 0 to d, and in our case d is equal to 2. So in a single iteration of the gradient descent algorithm, we update all the parameters once, and if j of theta is not minimum, then we run the algorithm as long as the value of j theta becomes less. So to get the value of this update rule, we need to resolve this derivative of j of theta with respect to theta j. So the partial derivative of j of theta with respect to theta j will be equal to, we have written the value of j of theta here, that's our cost function. We need to partially differentiate it with respect to theta j. So we'll write curly by curly theta j of 1 half summation I goes from 1 to n as theta of x for ith training example minus y of, that is the price of ith training example, whole squared. This is the sum of squared errors of n training examples. So to make the computation easy, we'll calculate the derivative for a single training example first, and then we will sum over the derivatives. So to do that, I'll write curly by curly theta j 1 half h theta of x. I will not write the superscript I here because this is for a single training example, whole squared. Now taking the differential of this squared term first, I'll take the 1 by 2 outside of the derivative. This will be equal to twice h theta of x minus y raised to the power 2 minus 1, that is equal to 1. And the internal differentiation of this, that will be equal to curly by curly theta j of h theta of x minus y. The 2 and 2 will cancel out. We'll get h theta of x minus y. We can write h theta of x as theta naught x naught plus theta 1 x1 plus so on up to theta j xj. Depends on the number of features, whereas j is the jth feature. And minus partial differentiation of y with respect to theta j, which is equal to 0. So now we get h theta of x minus y. As you can see, the partial differentiation of all these terms, theta naught x naught, theta 1 x1, will be equal to 0 except the term theta j xj, which will be equal to xj minus 0, which is equal to h theta x y xj. This is the derivative of a single training example. Now for n training examples, this will look like summation I goes from 1 to n h theta of x subscript I, that is the ith training example, minus y of y I into x j superscript I. This is the value of partial differentiation of j theta with respect to theta j. Now we can plug this value into our update method like this. Theta j will be equal to theta j minus alpha times summation I goes from 1 to n h theta of x superscript I minus y superscript I xj. Now this is the update rule that we use to update the parameters, all the parameters in a single iteration. In a single iteration, we will update theta naught, theta 1 and theta 2 simultaneously, and you can see to update a single parameter, we need to go through the entire data set and compute the difference between the predicted value and the actual value of a training example. That means if we have n parameters, then we will have to go through the data set n times in a single iteration, and if there are m number of iterations before the cost function becomes minimum, then this is going to be very costly. This type of gradient descent is called as batch gradient descent and is used for smaller data sets. To overcome this limitation, we'll see another type of gradient descent called as stochastic gradient descent in the next video. Thank you.